Have you ever wondered what could happen if we bring together artificial intelligence and quantum computers? Could this combo destroy our planet or give us a better understanding of the universe? What if the military starts using advanced artificial intelligence and quantum computers? Artificial intelligence has already become advanced, and scientists are tirelessly working to develop quantum computers. But what could happen when artificial intelligence and quantum computers join forces? Recently, the United States government pushed Google and NASA to stop their quantum computer development efforts. Why? Because they have noticed something terrifying. What's more interesting is that renowned physicist Michio Kaku has made an unsettling announcement about the potential dangers when quantum computers and artificial intelligence join forces.
So the two of them, the chatbots that are a revolution in software, and then quantum computers, which are a revolution in hardware, when they get together, watch out. So we're talking about an extremely powerful alliance between software and hardware.
Let's deep dive into the world of quantum computers, how they're set to revolutionize everything, and what terrifying announcement Michio Kaku has made. Quantum computers are a fascinating type of computer that depends on the principles of quantum mechanics to perform computations. Unlike traditional computers that use bits to represent information as either a 0 or a 1, quantum computers use quantum bits or qubits, which can represent information as both 0 and 1 simultaneously. This unique property is called superposition. The fundamental building blocks of a quantum computer are qubits. Qubits can exist in multiple states at the same time, thanks to superposition. This property allows quantum computers to perform complex calculations in parallel, providing the potential for exponential speedup compared to classical computers. To process and manipulate qubits, quantum computers rely on another principle called entanglement, which enables the correlation between multiple qubits so that the state of one qubit is directly related to the state of another, even if they are physically separated. This interconnectedness allows quantum computers to perform calculations on a large scale by leveraging the collective power of entangled qubits. Quantum computers are different from traditional computers in terms of their underlying principles and computing power. Traditional computers process information using classical bits, which are limited to representing information as either a 0 or a 1. Quantum computers, on the other hand, exploit the unique properties of qubits, such as superposition and entanglement, to perform computations in parallel and potentially solve certain problems more efficiently. The history of quantum computers begins with the development of quantum theory in the early 20th century. Quantum theory is a branch of physics that describes the behavior of particles at the atomic and subatomic levels. It introduced the concept of quantum mechanics, which challenged classical physics and revolutionized our understanding of the fundamental nature of reality. The key figure behind the development of quantum theory was Max Planck. In 1900, Planck proposed that energy is quantized, meaning it can only exist in discrete amounts or quantities. This idea laid the foundation for the understanding that particles, such as electrons, can only have specific energy levels. In 1925, Werner Heisenberg formulated the famous uncertainty principle, which states that the position and momentum of a particle cannot both be precisely determined at the same time. This principle reflected the probabilistic nature of quantum mechanics and highlighted the inherent limitations of classical physics in describing the microscopic world. Another major breakthrough came in 1935 when Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper presenting a thought experiment known as the EPR paradox. They argued that quantum mechanics appears to allow for the existence of spooky action at a distance, where the properties of entangled particles would be instantaneously linked regardless of the distance between them. However, it was not until 1980 that the concept of quantum computing emerged. Physicist Paul Benioff proposed the idea of using quantum systems to perform computational tasks. He suggested that quantum mechanics could be leveraged to create a new kind of computer that would harness the power of quantum phenomena, such as superposition and entanglement. In 1982, physicist Richard Feynman expanded on Benioff's ideas and speculated about the potential of quantum computers to solve problems that classical computers would find intractable. Feynman's visionary thinking sparked significant interest in the field and laid the groundwork for further research and development. Throughout the 1980s and 1990s, researchers made progress in understanding the principles underlying quantum computation. In 1994, mathematician Peter Shor developed a groundbreaking algorithm that demonstrated the potential of quantum computers to factor large numbers exponentially faster than classical computers. This discovery had significant implications for cryptography and the security of modern communication systems. The first practical implementation of a quantum computer came in 1998, where a research team at the Los Alamos National Laboratory built a 2-qubit quantum computer using nuclear magnetic resonance techniques. Although limited in its capabilities, this achievement marked an important milestone in the development of quantum computing. In the early 2000s, several research groups and companies began making progress in constructing more sophisticated quantum computers. One notable breakthrough occurred in 2001 when a team at IBM successfully built a 7-qubit quantum computer known as IBM Q. In 2002, scientists made progress in an area called quantum error correction. As we have discussed, when qubits interact with their environment, they can become unstable and lose their quantum state. Quantum error correction involves developing methods to protect quantum information from these errors. Researchers came up with new codes like the surface code that helped protect quantum information and make quantum computers more reliable. By 2005, researchers at the University of Innsbruck and the National Institute of Standards and Technology achieved an important milestone. They built a working quantum computer with 5 qubits. This was exciting because it showed that it was possible to create a practical quantum computer, even though it had a small number of qubits. In 2007, scientists at Yale University made another breakthrough. They found a way to create stable qubits using solid-state systems. This was important because it meant that quantum computers could be built using materials that were more stable and easier to work with. In 2010, researchers at the University of Science and Technology of China accomplished something called quantum teleportation. It might make you think of science fiction, but in this context, it refers to transferring the quantum state of one particle to another particle in a different location. The scientists were able to successfully teleport a quantum state over a distance of 10 miles. This was a significant achievement because it demonstrated the ability to send quantum information over long distances, which is important for building quantum networks. In 2013, Google and NASA joined hands to develop a quantum computer called the D-Wave 2. The plan was to install this cutting-edge technology at NASA's Ames Research Center. However, just as the project was gaining momentum, the government pressured Google and NASA to halt their quantum computer development efforts. This situation posed a major problem for the quantum computer project's progress. Unfortunately, it happened at the worst possible time. The D-Wave 2 quantum computer had already been turned on and was ready for use, but now its future was uncertain. Turning it off and on again when things returned to normal would have been expensive and time-consuming. So even though the computer was on, it couldn't be used to its full potential. It was stuck in a state where it was using electricity without actually doing anything useful for Google. This situation was confusing. They had invested in a special lab called the Ames Artificial Intelligence Lab, which gave them access to the quantum computer. But with the lab closed, they didn't know what they could do with it. A spokesperson from Google said that the computer was still working, but they couldn't provide much information about what they were doing with it or their future plans. Until NASA was fully operational again, the government shutdown had a big impact on the project. NASA's testing and exploration of this new and exciting technology had to stop. It was frustrating because they lost time and missed opportunities. The people working on the project were disappointed that they couldn't make progress and move forward. In 2019, Google made headlines again by announcing its achievement of quantum supremacy. They used a special quantum processor called Sycamore to solve a very complex mathematical problem. Regular computers would have taken thousands of years to do the same task. This breakthrough showed that quantum computers are much more powerful than classical computers for certain tasks. It also inspired other tech giants like IBM and Microsoft to work harder on building their own quantum computers. This created a competition to develop better and more reliable quantum systems. In 2020, IBM introduced the IBM System 1, the first fully integrated quantum computer made for commercial use. This was a significant milestone in making quantum computers more practical and available for a wider range of applications. As quantum computing research grew rapidly, it started attracting attention and investment from governments and industries around the world. Governments recognized the potential of quantum computers and provided funding for quantum research initiatives. This led to the establishment of quantum research centers and labs that encouraged collaborations between academia, industry, and government agencies. Modern scientists think that there might be intelligent life on other planets, but it's possible they're using black holes as super-powerful computers, which is why we haven't found them yet. The Fermi paradox has puzzled scientists for a long time. If there's a high chance that life exists elsewhere in the universe, why haven't we found clear evidence of it? The Hart-Tipler conjecture tries to explain this paradox by saying that if advanced alien civilizations existed in our galaxy, we would see signs of their activity everywhere. However, a recent study by German and Georgian physicists suggests a different idea. Maybe these civilizations are using black holes as supercomputers. Since the first search for extraterrestrial intelligence survey in 1960, scientists have been mainly looking for radio signals from faraway star systems. But this narrow approach might be limiting our chances of finding proof of alien life. Some researchers suggest expanding the search to other signs of technology, like directed energy neutrinos, quantum communications, and gravitational waves. The study by Jidawadi and Zaza Osmanov takes a different approach by exploring the idea of large-scale quantum computing as a possible sign of advanced alien civilizations. They suggest that black holes could be the ultimate source of computation for these civilizations. Quantum computing has big advantages, like processing information much faster and being hard to hack. Considering how fast quantum computing is advancing, it's reasonable to think that advanced civilizations would use this technology a lot. Scientists argue that black holes are the best places for quantum computing based on the laws of quantum physics and gravity. In simpler terms, black holes provide the perfect conditions for quantum computing. These hypothetical black holes would probably be made by aliens and very small to make computing more efficient. As a result, they would emit more intense radiation, including something called Hawking radiation. Hawking radiation is a theory by the late physicist Stephen Hawking, which suggests that radiation is released just outside of a black hole's boundary due to quantum effects. Jidawadi and Osmanov suggest that this radiation, including Hawking radiation, could be a sign of advanced alien civilizations. The emitted radiation would consist of different tiny particles, including high-energy neutrinos, which are small particles that can go through almost anything. So they would be great for carrying information and hard to block. According to the researchers, high-energy neutrinos could come from both the Hawking radiation of small black holes and the particle collisions used to create them. They mentioned the Ice Cube Observatory, a detector buried deep in Antarctica's ice, as a potential instrument to detect these signs of technology. This theory could explain why we haven't found any signs of advanced civilizations yet and resolved Fermi's paradox. If these civilizations have moved beyond radio and digital communication and started using black holes as computers, it would make sense that we haven't found any signs of their technology. Also, the fast progress of computing suggests that these civilizations might only use radio signals for a limited time. This lines up with their little parameter in the Drake equation, which represents how long civilizations actively send signals we can detect into space. Michio Kaku is a famous scientist who studies theoretical physics and shares his knowledge with the public. He is well known for his work on string theory and his expertise in explaining complicated scientific ideas in a simple way. Kaku often talks about advanced technologies and how they might shape the future. In his recent book called Quantum Supremacy, he explores the fascinating field of quantum computing. In a recent podcast episode, Michio Kaku discussed the impact of artificial intelligence chatbots and quantum computing. He explained that while artificial intelligence chatbots can generate thoughts and ideas, they lack the ability to determine what is true or false. On the other hand, quantum computers have the potential to check the accuracy of information generated by artificial intelligence systems, leading to more reliable results. However, Kaku expressed concern about the control of fact-checking capabilities, as governments could manipulate information and suppress opposing viewpoints. Quantum computing could either greatly benefit society or be used as a tool for deception and control, depending on how it is utilized. The development of artificial intelligence has been rapid, with significant progress made in artificial intelligence image generators and chatbots. However, there are hidden dangers associated with this technology. For instance, deepfakes can be used to spread false political information and make baseless accusations against individuals. The ability to create realistic images, videos, and audio recordings raises concerns about the authenticity of evidence and the resulting confusion. Artificial intelligence technology also poses risks in international conflicts, as deepfakes can be used to fabricate orders and create chaos among the public and armed forces. In law enforcement, artificial intelligence tools can contribute to excessive policing and biased decision-making, resulting in higher rates of pretrial detention and harsher sentencing, particularly for marginalized communities. The biases present in artificial intelligence models, influenced by existing societal biases, further worsen inequality. Furthermore, artificial intelligence language models can generate false information that could potentially cause harm. The stock market is also at risk from artificial intelligence trading bots, which could cause major disruptions. The potential for artificial intelligence to revolutionize internet searches raises concerns about the decline of the digital advertising market and the effectiveness of search engines. Scientists worldwide are working hard to create the first functional quantum computer, but it is a challenging task that may take several more years or even a decade to achieve. The timeline for its development depends on technological advancements, new discoveries, and the availability of resources. Scientists are working together to build quantum computers by combining knowledge from different fields like physics, computer science, and engineering. They use two main approaches: gate-based quantum computing and adiabatic quantum computing. In gate-based quantum computing, scientists manipulate and control individual quantum bits, known as qubits, to perform calculations. They are creating more stable qubits, like superconducting circuits and trapped ions, and finding ways to reduce errors and fix mistakes. Adiabatic quantum computing focuses on gradually evolving a quantum system to find solutions to complex problems using a phenomenon called quantum annealing. Scientists are experimenting with different materials and specialized devices to improve adiabatic quantum computers' performance and scalability. Developing quantum computers is challenging because they're very sensitive to their surroundings, which can cause errors. Scientists need to maintain delicate quantum states called quantum coherence for computation. Quantum computers also require a highly controlled and isolated environment with extremely low temperatures. Creating and maintaining these conditions is difficult and costly. The fragility of qubits and the need for low temperatures pose engineering challenges when scaling up quantum computers. Error correction is another important aspect. Scientists are researching ways to address errors that occur during quantum computations, which can worsen over time and affect accuracy. Implementing error correction adds complexity to the hardware requirements, making development more challenging. To overcome these challenges, scientists are collaborating and sharing resources. Governments, academic institutions, and private companies are investing heavily in quantum research and development initiatives like IBM Quantum, Google Quantum, Artificial Intelligence, and Microsoft Quantum provide access to quantum hardware, software, and educational resources for researchers worldwide. Continuous innovation in quantum algorithms and software also contributes to progress. Scientists are exploring various applications such as optimization problems, machine learning, cryptography, and drug discovery, where quantum computers have the potential to outperform classical computers. Scientists believe that quantum computers have the potential to revolutionize fields such as space exploration and the search for extraterrestrial life. The most significant aspect of space exploration is the immense amount of data that scientists and engineers must process and analyze. Quantum computers offer a tremendous advantage in this regard due to their ability to handle vast amounts of information simultaneously. Traditional computers process data sequentially, one piece at a time, while quantum computers utilize qubits, which can exist in multiple states simultaneously. This parallel processing capability allows quantum computers to solve complex problems much faster than classical computers. In the search for extraterrestrial life, quantum computers can aid in analyzing massive data sets from telescopes and space probes. They can quickly process and cross-reference vast amounts of information, searching for patterns or anomalies that might indicate the presence of alien life. With their speed and efficiency, quantum computers can help scientists sift through astronomical data and identify potentially habitable exoplanets, detect signs of atmospheric biosignatures, or even decipher complex alien communication. Quantum computers can also greatly enhance our ability to simulate and model astronomical phenomena. Space missions involve intricate calculations and simulations to understand celestial bodies and their interactions accurately. Quantum computers can perform complex simulations more accurately and rapidly than traditional computers, enabling us to gain deeper insights into the behavior of galaxies, black holes, and other cosmic phenomena. These simulations can help in planning space missions, optimizing trajectories, and predicting the behavior of space debris, thereby improving mission success rates and safety. Quantum computers also have the potential to revolutionize cryptography, which is a vital aspect of space exploration. Secure communication and data transmission are crucial for space missions, protecting sensitive information from interception or tampering. Traditional cryptographic algorithms, such as RSA, rely on the difficulty of factoring large numbers. However, quantum computers excel at factoring large numbers due to their ability to perform parallel computations. This poses a threat to conventional encryption methods. On the other hand, quantum cryptography offers a solution by utilizing the principles of quantum mechanics. Quantum cryptography provides secure communication channels immune to eavesdropping. It relies on the fundamental properties of quantum particles, such as entanglement and superposition, to ensure the integrity of transmitted data. Quantum computers can aid in the development and implementation of such secure communication protocols for space missions, protecting critical information from unauthorized access. Quantum computers may also contribute to advancements in propulsion systems for space exploration. Quantum mechanics enables phenomena like quantum entanglement and quantum tunneling, which could have profound implications for space propulsion. For example, quantum tunneling could allow particles to pass through energy barriers, potentially enabling more efficient and faster spacecraft propulsion. By simulating and studying these quantum phenomena, scientists could design novel propulsion systems that revolutionize our ability to explore distant celestial bodies. Quantum computers can also benefit the military in several ways. They can break encryption algorithms and strengthen secure communications. Quantum simulation and modeling can optimize logistics, design materials, and simulate nuclear reactions. Machine learning on quantum computers can enhance decision-making, pattern recognition, and autonomous systems. They excel at solving optimization problems, aiding in mission planning and resource allocation. Quantum sensors improve target tracking and detection, while quantum communication ensures secure channels for real-time battlefield analysis and data processing, enabling better situational awareness and informed decision-making. Although quantum computing is still developing, it holds significant potential for enhancing military capabilities. While quantum computers offer exciting possibilities for scientific breakthroughs and advancements in various fields, they also pose potential threats and challenges that need to be addressed. The most significant concern is the threat posed to encryption systems. Encryption is a fundamental tool used to secure sensitive information and protect data privacy. Many secure communication protocols, such as those used in online banking and government agencies, rely on the difficulty of factoring large numbers into their prime factors. Classical computers struggle to perform these calculations efficiently, making encryption secure. However, quantum computers have the potential to break these encryption schemes using Shor's algorithm, which can factor large numbers quickly. This means that the confidential information we rely on, such as financial records or classified data, could become vulnerable to malicious attacks if quantum computers fall into the wrong hands. Another area of concern lies in the field of cryptocurrency. Cryptocurrencies like Bitcoin use cryptographic algorithms, such as the elliptic curve digital signature algorithm, to secure transactions and ensure the integrity of the digital currency. Quantum computers have the potential to break these algorithms and compromise the security of cryptocurrencies. If quantum computers become powerful enough, they could potentially undermine the trust and reliability of cryptocurrencies, leading to financial instability and chaos in the digital economy. Quantum computers could also pose a threat to the integrity of the Internet itself. The Internet's infrastructure relies on public key cryptography to secure online communication, transactions, and data transfers. The use of quantum computers to break encryption algorithms could render these security measures ineffective, exposing sensitive information and creating opportunities for cyber attacks. This could have severe implications for e-commerce, online banking, and the overall trustworthiness of online interactions. Experts believe that quantum computers could also impact the field of data privacy. With their immense computational power, they could potentially unravel patterns and correlations hidden within large data sets, even if they are encrypted or anonymized. This could have significant consequences for individuals and organizations that rely on data privacy to safeguard personal information or trade secrets. The potential breach of data privacy by quantum computers raises concerns about the ethical implications and regulatory frameworks necessary to protect individuals' rights and prevent the misuse of sensitive information. In addition to these threats, quantum computers can undermine the integrity of scientific simulations and models. Quantum simulations have the potential to revolutionize fields such as material science, drug discovery, and climate modeling. However, if quantum computers become powerful enough, they could break the encryption of these simulations, allowing unauthorized access to sensitive information or altering the results. This could have severe consequences for scientific research, innovation, and decision-making processes. Addressing these threats requires proactive measures. Researchers and organizations are already exploring the development of post-quantum cryptography, which relies on encryption algorithms resistant to attacks from quantum computers. The transition to these new encryption methods will require careful planning and coordination to ensure the security of existing systems. Moreover, Investments in quantum-resistant technologies and encryption standards are necessary to prepare for the future. Governments and organizations should collaborate to develop robust solutions and establish guidelines and regulations to safeguard against potential risks. Additionally, international cooperation is crucial to ensure a unified response to the challenges posed by quantum computers.